Okay, here we are. Newton's laws practice problems. Number one, how does Newton's first law explain why you should always wear a seatbelt while riding in a car? So here we are, I guess that's me maybe, with my seatbelt on and driving. So if we just take Newton's first law and write it out, right? An object in motion, so what's the object here? So an object, let's redo this again. So the person, right? So the person in the car is in motion and will stay in motion. Stay in motion until acted upon by an outside force, right? Until acted upon by an outside force. Yes, I'm writing it all out. Okay. Yeah, if your car is going 30 miles per hour, you are also going 30 miles per hour with a car. And what's going to keep you in motion, right, even though the car stops, is your inertia, right? So your inertia will keep you in motion at that 30 miles per hour. Now, if the car stops and hits something, obviously whatever it hits is going to be the outside force. Maybe it's another car, maybe it's a rail or something. But then your inertia is going to keep you moving forward, right? You're going to stay in motion. And we have some choices, right? You know, we really want that outside force to be the seatbelt, right? We don't want it to be the steering wheel, the windshield. We want to keep you in the car. So the seatbelt is going to provide that outside force to bring you to being at rest from in motion. Okay, number two, why is mass more fundamental than weight? So we know that mass is just constant. So your mass is the same wherever you go. It's the amount of stuff that makes you up. But weight depends on what you're standing on, right? Weight, it's really just another word for force of gravity. So we know the force of gravity depends on two things, right? If we look at Newton's second law, force equals mass times acceleration, where that acceleration rate here, or little g, is the acceleration of gravity of what you're standing on, right? And for all of us, it's the Earth. For a few lucky people, it was the moon. And maybe for some luckier people in the future, it might be Mars, right? Speaking of Mars, let's take a look here and calculate some weights here. So it says, hey, after watching the movie The Martian with Matt Damon, his mass is 84 kilograms. Hey, you wonder what his weight is on Mars. We should calculate his weight on Earth just for a comparison, right? So if his mass is 84 kilograms, his force of gravity or weight on Earth would be his 84 kilograms times Earth's gravity, which is 9.8 meters per second squared. And so if I do that out really quick on the calculator, and you can do it right now with me, 84 times 9.8 gives me about 823 newtons, right? Not pounds, not kilograms. You know, I think this is one thing we're not really familiar with, the units of force in the metric system of newtons, because you would obviously say your weight in pounds. If you meet someone from overseas, they're going to tell you their mass in kilos, right? Newtons is just kind of a foreign term that we're just not familiar with, but that is the metric unit of force. So let's see what his force of gravity or weight would be on Mars. Again, his mass is constant, not going to change just because he's on Mars. But Mars isn't as big or massive as the Earth, so its acceleration of gravity is less. It's only 3.8. So if I do that out, that's going to give us a weight of about 319 newtons. So you can see Matt Damon's, he weighs less on Mars than he would weigh on Earth. But if they were actually going to plan a sequel and go to Jupiter, it would be called the Jovian, right? An alien from Mars would be called a Martian. An alien from Jupiter would be called a Jovian. What would his weight be? Not that he could stand on Jupiter because it's a gas giant planet. But if he could stand on there, what would his weight be, right? So again, force of gravity or his weight is equal to mass times acceleration due to gravity. He's still 84 kilos no matter where he goes. But now the acceleration due to gravity on Jupiter is 25. And if we work that out, that's going to give him a weight of 2,100 newtons on Jupiter, right? Jupiter is a lot bigger. It's the largest planet in our solar system. You could fit the Earth inside the Great Red Spot here about 2 to 3 times. That's how big the Great Red Spot is. So it has an acceleration rate of nearly, well, about 2.5 times that of Earth, right? Okay, last one here with number 4 with some action-reaction force stuff and drawing that stuff in. I'm going to do it all in red. So head bumps ball, and head's bumping the ball this way. So the reaction force would be that the ball bumps the head, right? You're going to feel the ball pushing on you, and that's the force of the ball on your head. It's going to push on your head this way, right? I'm careful to draw that arrow in the opposite direction, but equal in length to the other one, right? Because for every action, there's an equal and opposite force. Number 2 here, it says bat hits ball, and the bat pushes the ball this way. Well, if you were swinging the bat, you would feel the ball pushing back on the bat. And that force would be in the opposite direction and equal in size. So again, I draw that arrow the same size. If you're going to go out and pull some flowers, it's not springtime right now, but that would be hand pulls flower this way. You're trying to pull it out of the ground, but you're going to be met with some resistance, right? The flower is going to pull back on your hand. And that is going to be the reaction force. Flower pulls hand, and it's going to pull this way by the same amount. Okay, thank you for some practice on Newton's 3 laws.